All right, so let us push on. So in line with the definition of the one-to-one mapping, what would be done there is that the first element here will map with the other element. The element of the domain is assigned to one element, assigned to one. So this is assigned to this, this is assigned to this, this is assigned to this. So one element in the domain must be assigned to another element in the other domain. Sometimes it mustn't be exactly this way. So, but there must be an assigning. A now can be assigned to Z, and then C assigned to this, and this assigned to this. Let me take that again now. For example, if we have it this way, let me draw a smaller one here because we don't have that space. X, Y, and Z. This can be assigned to this, this can be assigned to this, and this assigned to this, provided they are assigned. That is what we call one-to-one mapping. Yes, James. James.
So, mister, the board was kind of blurry. I couldn't see it clearly.
But it's better now.
Yes, but as it is better now, it will go blurry.
Okay, I guess it's.
I don't know why.
It's actually network.
That's always
It's
been
network.
like that now.
Yes, it's network. All right. So that is how the one-to-one mapping is, just for you to know. So every element, each of the elements in the domain, which is the first set, must be assigned to an element in the second set. Each element in the domain must be assigned to an element in the other domain. That is for one-to-one mapping. So I want to take the second mapping. The second mapping was an onto mapping. All right, so the onto, well, we have subjective. The subjective mapping. The subjective or the onto mapping is that type of mapping where every element in the codomain is at least an image of the element in the domain. Now that we have known what domain is, the domain is the first set, and the other one, this is the domain, this is the codomain, this is the domain, the codomain, and the onto or subjective mapping. In this type of mapping, this is what happens. Every element in the codomain, is at least an image of the element in the domain. Now I am going to explain that. So if we have this as the domain and this other side as the codomain, let me write that out. Let me draw this well. This is the domain, and we have the codomain. We have these elements, for example, A, B, C, D. If we have those elements, and we have the other one, W, X, Y, and Z, as the elements in the domain and the codomain, respectively. So what happens here is that every element in the codomain is at least an image. It is at least an image of the domain. So that means we can get this element to map with the other element in the codomain. This can map with this. Can put it this way or the other way. This is mapping with this. A is mapping with W and B mapping with X. Are you following me? Then the next is that this will map with this, and then this will map with this. This is the onto or surjective mapping. The onto or surjective mapping. We can also have the mapping this way. The A and the B, you see I have the same A, B, C, and D. W, X, Y, and Z. If we still have it this way, this is the domain, and the other part, the codomain. It can also map this way. This can map to this. This can map to this. And then C maps to X. B maps to what? To Y. So it can either cross at the middle, cross somewhere upwards. This also means that we can also have a mapping this way. If we have A, B, C, and D, then we have W, X, Y, and Z. For example, the mapping can also go the other way. Remember this one was down, so we can have A mapping this, and we can have B mapping this way. We can have C mapping this, and this mapping this. Did you get that? That is for the onto or surjective mapping. The onto or surjective mapping. Onto or surjective mapping. Yes, silver line.
Good evening, sir. Sorry.
Yeah, good evening.
I'm just a bit confused because yesterday we were saying if we have the same elements in the two but today now you are doing is it that the mapping doesn't matter?
Take that question again. Is it if we have the same
anyhow or what?
Take the question again. If we have what?
Okay. Concerning yesterday's class, you said if we have the same element in both sets, which is set A has 3 elements, then set B has 3 elements. The two sets can map each other like straight mapping. And today.
And what did I call the type of mapping?
We were talking about operators, transformation, and
look, that's why I said let us all pay attention. What I'm talking about now, I'm talking about types of mapping. So, but now what you are relating, you are talking about operations and transformation, which we did yesterday. So I just want you to pay attention to this and get it, connect it to what we had yesterday. That's why, while I was talking, I said let's all pay attention first. Then we can now bring up our question. So I was expecting that probably what you would be asking for is that you mentioned yesterday about equality or equal functions. When I did mapping yesterday, I said that mapping or function describes how elements from one set are related.
I can't hear you.
I said yesterday I said that in respect to mapping of functions, that mapping is meant to describe how elements in a particular set, from this set now is what? From one set are related. Related now. This set now is relating to this other set. That is what we call mapping. That's what I said yesterday. So, and I went on to try to talk about operators and transformation. What I am talking about today now, I am talking about types of mapping. A little bit away from what I said yesterday. So don't be confused. Did you get that? All right, Ola.
Yeah, thank you very much, sir.
Yes.
Yeah, my own question goes like this. If the code domain and the domain, if element is more than it could have, so I'm going to mark it like yesterday one, like maybe we have 5 elements, we have 4 elements on the other side, or we have domain 4 elements and we have a code domain 5 elements.
Okay, that is why I said we should all hold on. So let everybody hold on till I'm done. Let's hold on. When you, as I keep going, you understand it. Just be patient. So that is for. So one thing I want you to know when you are learning, try to follow the teacher. Now I've told you about the one-to-one mapping. Take note of that. What does one-to-one mapping mean? Put it in your mind. Just like when we're doing numbers, types of numbers, we talked about real numbers and integers and all that. You see that this one was connecting to the other one. So just pay attention and you'll be able to get what you need to get. So let us go to the next one. The next type of mapping. The next is identity mapping. So I'm taking this one out now. I will now talk about identity mapping. Identity mapping. In connection to identity mapping, even the mapping I just finished talking about, the onto mapping. On the onto mapping, it has a kind of connection to the one-to-one mapping because every element in the domain is a mirror, is a reflection, is a connection to the element in the codomain. That is in respect to the onto, that is the subjective mapping. It has a relationship with the one-to-one mapping. So in the identity mapping, for example, if an element is mapped, to itself in a codomain, if an element is mapped to itself in a codomain, it is called identity mapping. Now I'm going to explain that. If we have these elements, element A and element B mapping, and it is put this way, we have the map this way, we have the other map this way. This is set A and B with their various elements. So we have here A, B, and C. In this type of mapping, the elements it will map itself. Remember, this is the domain, and this part is the codomain. The domain and the codomain. So this is what happens. We would have the elements rearranged, not this way. It's going to now be what? C, B, A. So this is how the mapping will be done. So I would like somebody now who is very smart enough to look at the statement that I made. I say, if an element is mapped to itself in a codomain, it is called identity mapping. So can somebody just confidently say, okay, this is how we are going to map this to this? So would anybody, okay, yes, Roland, your hand is up. Just tell me how we can map it. Roland.
Okay, so we are going to say A will map A in the codomain.
Okay.
Just draw the line from the domain A to A.
All right. A to A. Awesome. That's exactly what I
B
want.
to B.
Yes. Then B
Okay.
to B. B to B. Then what?
And C to C.
C to C. That is just what it means. So once you read the words and you get it rightly, then every other thing is straight to the point. It is just for you to, that is why I take out time to just write the notes. So when I write the notes, you on your own now, when you are reading, you can now make notes. You make notes and it will help you to understand it better. I think that's one of the things they said in a GST, is it GST 107, first semester? It talked about making notes. So it's very important that when you study like that, on your own, make notes. That's how I study too. So if I don't study, I will not be able to teach. So the words there, I've already told you how the mapping will be done. So in this case now, it is this way: A mapping A, B mapping B, and then C mapping C. That's how it is. Unlike the other cases where we would have A mapping, maybe A will be mapping B, and C will be mapping A, the other way around. That's for the other one-to-one mapping. But for identity, like the name implies, it identifies its co-domain. The element from the domain we identify is a mirror. It will identify the element in the co-domain. It says, this is my brother. Then it takes it and what? And map with it. That is that about identity mapping. So now let us look at the last one, constant mapping. Let us look at the last one, constant mapping. Constant mapping. In constant mapping, something happens. It occurs when every element in the domain maps, when it maps with a constant element in the codomain, we call it constant mapping. That's what we call it. We call it constant mapping. So let me write that out. So it occurs when every element, take note of the word every element, like I always do, every element in the domain is mapped to a constant element in the code domain. That is when we have what we call constant mapping. Constant mapping happens when every of all the elements, every element that is in the domain. So this is the domain. This is the codomain. So it means that every element in this domain will be mapped to a constant element, to a particular element in the codomain. All the elements in the domain will just go and map a particular element in the codomain. So for example, if we have A, B, and C, and then we have S, T, and U, from what I have written in the board in line with the definition or explanation of constant mapping, what do you think would be the mapping in this case? Yes, James. James, go ahead.
To me, concerning the question, I think let's assume A will go to T.
A will go to
T, letter C, in the codomain.
Okay.
Then B will go to letter C in the codomain.
B will go to what? Letter T.
B will map
C in the codomain too, and C the same thing.
Okay, C the same thing. Awesome. That is exactly what it is. That is constant mapping. So every element in the domain, which is this, the domain, here the codomain, every element in the domain is mapped to a constant element. This is the constant element. I like it keeps going there. So if it is not mapped this way, that means A, B, and C can decide we are mapping only S. A, B, and C can decide we want to map only what? U. Did you get that now? So it doesn't matter if the elements in the set are not equal. Even if they are not equal. For example, if we have this, if we have the domain having just two elements, for example, A and B, and the codomain having these elements 1, 2, 3, 4, we can as well have the mapping to happen this way. This mapping, A mapping 1 and B mapping also what? 1. So this is the mapping. So it doesn't matter whether they are equal or not equal. So I mean, how you would arrange this, you can now say that what A is mapping T, B maps T, and then C also maps T. In this case, this is A mapping 1 and B mapping 1. That's the way it is for constant mapping. Silverline, are you following?
Yes, sir.
All right. So I hope everyone is following, and it's very simple. So if you understand each of them one after the other, then you wouldn't have any problem. But now the question may come now, how would they bring up these questions in the exams? For example, you may see a diagram like this, and the mapping is done already, and they put amongst the option, what type of mapping is this? So maybe they say option A, 1-to-1, option B, onto, option C, constant mapping, option D, identity mapping. So what you should be able to know, now that you have seen how each of them are mapped, you should be able to know, in line with the definitions and explanations that I've given, you should be able to know, okay, this one is actually constant mapping. The other one is 1-to-1 mapping, and this, I mean, just like that. That's how to know about this mapping. But now we go to the beautiful part of it. We go to the beautiful part of it, and what we have done so far will help us to be able to understand the other part that we are about to go into, and that's equal functions. Now we are entering into function itself. We're entering into function itself. So I want you to give good attention so that you can get it rightly. I know we treated equal function a little bit yesterday, but now we are going to touch it deeper. We are going to touch it deeper so that it can be clearer for those of us that were not here. So equal functions. Equal functions. So a function is said to be equal when they have equal domains. Like I said yesterday, I think one of the things, I guess that is where Silverline was actually trying to go to. That I said that this must be equal to the, like, having the same element. Do you understand? So, but there's a deeper part of equal functions I want you to see, swaying away from what we talked about yesterday. So, but in this case now, a function is said to be equal. It's said to be equal when they have equal domains. When they have equal domains. See it now. They have equal domains. For example, this particular one now, I want you to look at the board very well. For example, if domain of f, we are talking about function now, so take your mind a little bit away from what we have just done now, because it's talking about functions. So f here now stands for function. So for example, if the domain of function f, this function is equal to the domain of the function g, is equal to the domain of the function g. So we say, in this case now, this is how it's written now. This is like putting it this way. Let me separate it now. F is equal to g. F is equal to g. That is this function f has its own domains, has some set of elements, and function g also have some set of elements, which is also its domain. The equal function tells you that the domain of f is also equal to the domain of g. Whatever you have in the function f would also be equal, this time not necessarily the same types of members, but in respect to function. So now, follow me carefully now. So if we also, okay, this is for 1, let me say that as 1, 2, the codomain of this function, of the function f, is equal to the codomain. Is also equal to the codomain of function g. This is a function, that g is a function. It also means that what? F is equal to g. Usually this is how function is denoted. Function is denoted this way. So take notes. This is how functions are denoted. So you say f is a function of x. G is a function of x. F is a function of x. G is a function of x. This is how function is denoted. So in this case, we are going to say what? The function of x is equal to what? The function of g. G as a function of x. F as a function of x is equal to g as a function of x. That's what it means in this case, in respect to equal functions. So these functions are equal. These are functions. This is how functions are denoted. Functions are denoted this way. It can be like this. It can even be ish. But what you see very, common is what? Is f and g. So take note of that. So it means that the elements, the sum of the element, or the value of the element of this function, is equal to the value of the element of the other function. What that means, if I have this as my domain for function x, for the f as a function of x, and I also have another one as my domain again. So this time around, it is not domain and codomain. I have for gx. So this is the function of x. For this is the domain of the function of x. This is the domain of the function of g. Are you following? So now, if this man now has these elements 1 and 2 in its domain, and the other man has the elements 1, 2, 3, and 4. 1, 2, 3, and 4 as the elements in its own domain. So look at this time now. It doesn't look like they are equal, in line with what we were talking about yesterday. So how this is mapped, I am going to prove the mapping for you, so don't get carried away, just give attention. 1 is mapped with 1, and then 2 is mapped with 4. So how did we get this? How is this mapping done? Now look at it very well. I'm taking this part out. So if we say that the function of x is equal to g as a function of x, for example, like we said yesterday, in respect to equal functions, what you have, if we have an equation like this, if we have a function like this, if we have the function of x equal to x squared plus 2, and the function of g equal to 3x, if the function of x is equal to this and the function of g is equal to this, and you are telling me that in respect to equality of functions or equal function, that fx is equal to gx, how do you prove this? How do we prove this? Now that's the question in our mind now. So if we have set A, according to what we have here, set A representing this domain, to have the elements 1 and 2, and set B to have the elements, for example, 3 and 6 now, 1 and 2, and then 3 and 6. How do we prove this, that the function of x is equal to g, the function of x? So what you are just going to do is that for each of, so A now, A is actually what? Mapping f, this f is a function of this, and g is for what? B. In this case now, this is the domain, this is this domain. So what you are going to do now is to substitute the value of the domain for the function of x, for f the function of x and g the function of x. So what you are going to do now, in this case, you are told that f is equal to x squared plus 2. And one of the elements in this part is actually what? X is equal to 1. And the other element is what? X is equal to what? 2. So let us see now whether this domain is equal to this domain, just like we have here, equal to this. So we are going to substitute the value 1 into this function. So that means you put it like this. So we are taking x 1 as a function of x. So anywhere you see x, you are going to replace it with 1. So you come here, 1 raised to the power 2 square plus 2 is equal to, so 1 raised to the power 2 is what? Is 1. So that is 1 times 1 is 1 plus 2. What is it equal to? 3. So which is this? Are you seeing that? So that's to show you that the first element is equal to the what? The second, the domain here, the first element of this domain is equal to the other element in this domain. So now let's go to the next one. Let's take care of the next one. So since we are told now that g as a function of x is equal to 3x, g as a function of x is equal to 3x, and you are told that x is 1. So let us look for it now. So we put that g1 is equal to what? 3, 1. So which is what? 3 times 1. So 3 times 1, so 3 times 1 is equal to what? 3. So in the first case, the function of x is equal to what? G, the function of x. That's for the first case now. 1 to 3. So 1 to 3. So when you substituted 1 into the function here, x squared plus 2, it gave you 3. when you also substituted 1 for x into this function, gx is equal to 3x, which is what we have done here. You also got 3. So let us try it for the second one. Let's try it for the second one. So for the second, we have f2 is equal to 2 square plus 2. So 2 square is what? 4. That's 2 times 2 is 4. 4 plus 2 is what? 6. So let us substitute that same 2 into this function now. Into the function gx is equal to 3x. And so we have now g2 is equal to what? 3 and 2. So which is equal to 3 times 2. What do we still have? We have 6. Did you get that? We have 6. So this proves to us that f, the function of x, is equal to what? G, the function of x. So they are equal functions. They are equal functions. Did we all get that? Is there any question around what I've explained so far? Did we all get it?
I got it, sir.
All right. So let me assume the quietness is that we all got it. Let me assume the quietness is that we all got it. So now let us represent it in mapping form. Let us map this particular information now. So if I'm taking out this, and I have this domain and another domain, we have what did we have there? It was 1 and 2 and then 3 and 6. What that means is that this maps to this and this maps to what? To this. So they are equal functions. So which means this was what? Function x, and this other part was what? Function g. So the function of x is equal to what? The function of g, which was what did we have as the function of x? The function of x was x squared plus 2 is equal to what? 3x. Did you see that? So x squared for this is equal to what? 3x. So this is how it is denoted. So you are going to write it this way. F mapping A to B, and then G is mapping A to what? To B. That's how it is written. That is how it's written. Very beautiful mathematics, very sweet. I even like this equality. The equality will even make it very easy for you. But let us try one more. I think we did one yesterday, but let us try one more and see if they are actually going to be equal. So if we have, I want to take the question the other way now. If we have the mapping this way, with what we had here as f, the function of this is equal to this plus 2, and gx is also equal to what? 3x. You can also use this to what? To make that proof, but not in relation to this now, not in relation to this because of the kind of elements you have. So in this case now, fx, what we had yesterday, is equal to what? Gx, where fx is equal to x squared, and then gx is equal to what? Also x squared. So if we substitute the value of the domain towards the other domain, which is this A and B, what we are going to have, if we take the first one and we say, for example, if we substitute 1 into the value x for the function x, what you are going to have, let me take out the first part. So if we have fx is equal to x squared, and where x is equal to 1 in this case now for the first domain for this function now. So if you substitute it for f1 is equal to 1 squared, your answer is going to be equal to what? 1, which is 1 times 1. 1 times 1. So this is 1 to 1. This one is a mirror of this. This is mapping this. So let us substitute it for gx. For gx, for g as a function of x, we are going to have g1 is equal to what? 1 squared, which is also equal to what? To 1. Same thing. So for 2, we do the same thing. For 2, we do the same thing. So let us bring it into the expression. Let's bring it into the expression. So we have function of x is equal to x squared. Then 2 as a function is equal to what? 2 squared, which is equal to what? 4. That is 2 times 2. Then for gx, which is also equal to what? X squared. What do we have there is g2 is equal to what? 2 squared, which is also equal to what? To 4. So 2 is equal to what? To 4. Anywhere you are substituting 2, it gives you the value 4. Did you see that? Yeah?
Yes, sir.
Yes, Damilola, you wanted to say something? That's good. Yes, Dami, go ahead.
Oh, sorry, sir. It was a mistake, sir. I'm sorry.
Okay, very well. But do we all understand what I have just done? Did we all get it?
For me, I got it.
No more.
All
Yes,
right,
sir.
very well.
Yes, sir. Yes,
Okay.
sir. I got
Okay.
it, sir.
All right. Memunat, how is it going, Memunat? I've not heard your voice. I miss your voice.
Good evening, sir. I'm just trying to learn some things.
Okay, trying to catch up. All right. It's a very beautiful
I am
one.
not prepared, so I know that I will get it fine.
All right, no problem. So I have even tried the recording will be available, and it will be straight to the point, so we can also get it rightly. So no worries anyway. So let us go. Let us now, we are moving to range of function, and that is the last one we are going to be doing today, range of functions. All right, so let's look at range of function. This thing is a general class. Yeah? So range of function, let me just write it out. that will not enter the video. All right, so range of function is, it actually refers to the set of all possible outputs. The output now is the codomain. The codomain is the output value that the function can produce for the given input. The input is the domain. So the domain is actually the input that you use to work to give the output, which is the codomain. So in this case, the domain is the input value, while the codomain is the output value. That's exactly how range of function works. Range of function works that way, almost a little bit into what we have in equal functions. For example, now, if we have the function of x, f the function of x equal to x squared, if x the function of x is equal to x squared, for domain in this case now, in case of range of function, is the set of all real numbers. Do we remember real numbers? I'm going to ask question there, what real number is. So prepare. Real number, x can be in bracket there, x can be any real number. This is the output now. The domain is the output. Then for codomain, which is the codomain is the output, while domain is the input in this case now. Sorry. So the codomain is the set of all real numbers. X also in this case can be any real, x can be any real number as well. So the input will be a real number, the output will also be a real number. If the input is not a real number, the output cannot be a real number. So the first thing that should come to your mind is that what is a real number? If you now know what a real number is that in respect to range of domain, you don't have anything as fractions. You don't have fractions, so you have what? Real numbers. The real number in this case is x. So even if you have a fraction-like function, for example, if you have a function like this, what they are telling you that in this function, the x must be a real number. So don't be carried away by the statement that I made that you said real number, so why are we not having something like this as a fraction? In this case, the real number that we are referring to, that is why I put it in bracket. I says x can be any real number. So you may have a function like this. For example, you may have a function like this: x squared plus x minus 5. This is a function. So this function now, if this function now is the input should have a real number replacing x. That is what I'm trying to say. So all values of x must be a real number. That is the meaning of what I am trying to say. I don't know if we all got that. All value of x must be a real number. So let me take that up. Let me quickly take that up now. So like we said now, if f, the function of x, is equal to x squared now, in this case now. So let us assume, so what is real number now? Can anybody tell me what a real number is very quickly? What is a real number? Yes. Sharp one.
real numbers include both rational and irrational numbers.
Okay, I want it more precise because now you have just said it like a mathematician. So if somebody who doesn't understand what rational and irrational number is, the person will not even connect it. Okay, so James, go ahead, James.
One, two, five. The real numbers are the non-negative numbers.
Okay.
And they have no fraction. Points.
All right. Okay. I think that is helpful. Okay, let's all mute our mic now. So let us call out some real numbers now. Maybe I said real numbers for x. Real numbers for x is equal to, let me start from -2, -1, 0, 1, 2. So these are real numbers. So real numbers are numbers whether they are positive or negative, including zero. They can be like Roland said, they can be rational or irrational numbers. So they can be either negative or positive. So if the real numbers for x is -2, -1, 0, 1, and 2. So what you are told to do now in range of function is to substitute. What you are just going to do is to what? Is to substitute the value. So what you do now, so let's plug in. So this is the function fx is equal to x squared. So let's take the first real number. So the first real number is going to be what? The function 2 is equal to what? 2 minus 2 squared. Ensure you put the signs. So for the function of -2, we have there what? -2 times -2. What's going to be the value? What's the value? -2 times -2. Yes, James. -2 times -2 is 4.
-4.
Is 4 plus 4. Yeah, so minus times minus is equal to what? Plus. Did you get that? Always don't forget this. So your answer is 4. So the range of function, so this is how you now state it. The range of function where the real number is -2 is equal to 4. So let me write that out. It maps to 4. It maps to 4. So that means the function 2 is actually mapping 4. Did you see that? The function of -2 is actually mapping 4. So you can substitute for each of them. You substitute for each of the real numbers that is provided for you. So if we substitute for this, maybe at this angle now, let me use this space. If we substitute for 1, we are going to have -1 is equal to -1 squared. So which is equal to what? So the function of -1 is equal to what? 1. So we write it like this. 1. So for 0, we just put 0. Then we have what? 0 squared. So the function there is equal to what? 0. So we have for the function of 0, it's mapped to what? To 0. Did you see that? It's mapping to 0. So for how about 1 also, we still come back to what? 1. It's the same thing apart from the sign. still mapping to what? To 1. Then the last one, which is 2, we also still map to what? To 4. So the function 2 we also map to what? 4. So we can actually represent this in a what? In a map. So let's try to see if we can, let's put it in the form of a map now. So if I have this map and I have this, the element in the first set of real numbers, we had -2, -1, 0, 1, 2. So we have -2, -1, 0, 1, and 2. Then we also have this other part now. We have 1, 1, so we have 0, 1, and 4. That's just so you don't need to write, you don't need to repeat elements. You remember that now. So let us map it now. Let us map it together for -2 to 4. So -2 to 4. This is how it maps. Then -1 to 1. -1 maps to 1. Then 0 to 0. 0 map to 0. Then 1 to 1 again. It's 1 to 1. Yeah. Then 2 to 4. And this is the 2 to 4. Did you see the mapping? I hope that's very clear for every one of us.
I hope that's very clear.
So, do we have any questions so far with what we have done? Any question? Hello?
No question for me, sir.
All right. So, any question is like we are all clear. Today's class is very smooth and very sweet. So, we are going to take one more to take care of range of function. I'll try one more example. I'll try one more example in respect to range of function now. So if we have the function and you are told to find or say evaluate the range of a function for the real number. Let me say 2 and 3 for the real numbers. So numbers now. For the real numbers 2 and 3. So for this function, evaluate the range of function for the real numbers 2 and 3. So what we are expected to do in this case, is just to substitute the value. It's a very straight thing now. So you bring down the function x is equal to 2x squared plus 2x plus 1. So we take the first real number, we substitute it. We say the function of 2 is equal to 2 raised to power 2 plus 2 here. You are replacing anywhere you see x, you put the first real number plus 1. So you have there the function of 2 is, this is 2 times 4. That's 2 raised to power 2 is what? 4. Plus 2 times 2 is what? 4. Plus 1 is equal to 2 times 4 is 8. Plus 4 plus 1. So what's your final value there? 8 plus 4 plus 1. This is 12 plus 1, 13. So your final value there is 13. So for the function, the range of function for this particular function is what? Is 13. So for this range of function for 2 is 13. So let us try it for 3. So we go ahead, do the same thing. 2x squared plus 2x plus 1. So we substitute the value 3. You have 2, 3 squared plus 2, 3 plus 1 is equal to 3 raised to the power 2 is 2 times 9 plus 2 times 3 is 6 plus 1. So we go ahead, 2 times 9, 18 plus 6 plus 1, 7. So what do we have as our final answer? 18 plus 7 is 25.
24.
Is it 24? 25. It's 25. 25. So you can actually still map it. So let's map it now. We have 2 and 3. And then we have a 13, 25. Two and 3, 13, 35. So 2 maps 13 and 3 maps 25. Very good, very sweet, very awesome. I'm expecting A1 from everybody in this class. Yes, James.
Okay, so please concerning the last element on the domain on both the domain and the codomain. Is it okay if they change it, like if they change the position of that 13 to 25 and to take over the position of 13?
Okay.
Is it okay to cross the
So let's say this is what James is saying.
exactly, sir?
Yes. Provided it is mapping. Provided it is mapping, then you are good to go. Yes. Okay, so I'm going to drop some assignments that we are going to run with for the week. We'll run it for the week. So if you submit in time, then we are also going to have it attended to in time. So just keep practicing. The more you practice, the more you get used to it. We're told in biology, the more you use an organ, the more it gets enlarged. So just keep practicing. Everything is going to go well. So that's where we are going to stop for this evening. I wish you all a pleasant weekend and enjoy your new week. God bless you. All right. Bye-bye.
Thank you so much.
Thank you very much, sir. Amen.